Good morning, everyone. It's a real delight to be here today and an honor to have been asked to moderate this first part of our four-part spring meeting series on environmental dynamics and exposure pathways of subsurface contaminants. Now, before we get underway, as Teresa promised, I wanted to give a little bit of context and background to how we came to this four-part series, and your important role in that is the launch meeting for the series. Teresa and I, as you know, each oversee two boards, and earlier this year, back in January, we were having some discussions about some common areas of interest and common problems we see when talking about subsurface chemistry, subsurface geochemistry, geophysics, geomechanics, scaling issues, both temporal and spatial and so forth. And those conversations were seeded by some separate discussions we were each having with colleagues at the Department of Energy. And as these conversations progressed, we thought, well, wouldn't it be interesting to try to link the different components that each of our boards has in this broad umbrella space of subsurface contaminants, using the mechanism of our already scheduled spring meetings and conduct that in sort of a four-part series. So that was basically how the idea was launched. Now, in a certain sense, the fact that the topic is an interdisciplinary one, obviously. So in an ideal way, one would have liked to have these conversations over a continuous set of days, perhaps. So ours are separated in time, and the way that we're trying to help link common threads through that time difference is through this one question: what are key challenges and advances for assessing the quality of the subsurface environment and managing risks? So all of the talks and each of the sessions is going to have certainly its own focus, but we're going to use that common question as a thread that links these different meetings. And each board then is going to be addressing this topic through its particular lenses. Today we're going to be looking mostly at the molecular level, of course, with the aspects that the Board on Chemical Sciences and Technology brings to the subsurface and contaminant transport. In early April, the Board on Environmental Studies and Toxicology is going to be looking at approaches for characterizing exposure pathways and then linking those and contaminants to humans and ecosystems. In later April, the Board on Earth Sciences and Resources is then going to be taking the facet of linking the fluids and the rock matrix. The rocks are filled with cracks and faults and fractures and grains and boundaries, and so we're going to be trying to look at that interface between the rock matrix and the fluids. And then finally, in May, the Water Science and Technology Board is going to take us back to water, and specifically groundwater contamination. So again, each of the boards is going to be looking at a unique facet of this problem, but we're trying to link those elements together. The subsurface isn't for the faint of heart. It's very, very complicated. And so we hope that with this faceted approach that we're going to be highlighting some common problems, maybe some unique problems, and helping to nudge the discussions a little bit farther forward, both for our federal colleagues, because this is not only a topic of interest for the Department of Energy, but it's a topic of great interest for colleagues at the National Science Foundation, EPA, DOD, certainly NASA, and others. So we're hoping to help the federal family as well as practitioners, the academic community, industry, and so forth. We're also hoping to gain some new friends and colleagues with each of our boards. So you will be hearing from us again at least 3 more times, because we're sharing our listservs and our advertisements for these meetings. So we're trying to push the advertisements for each of the meetings to all of our boards and all of our boards' networks. And so today we had a large registration with our online participants, and part of that is driven by having reached out not only to BCST's friends, but friends of the other boards. If folks aren't able to plug in live to either in person or via the webcast, because each meeting will also be webcast, we're going to, at the end of all of this, in June, be knitting together each of the webcasts into a single webcast, which will then be posted on our website so that people can dip in and either relive an experience or experience one of the events that they weren't able to visit. So again, this is highly experimental. We'd be really interested in your feedback, because these are the kinds of things you were all informed about some of the new approaches the Academy is going to be trying to take in the future. This is maybe one example of that. So again, feedback would be really welcome. The other part that I want to do is obviously this sort of multi-board, multi-ring circus doesn't occur in a vacuum. There are a lot of staff who are various components of this, and I wanted to acknowledge there are staff in the room here who have been involved and will be involved in this going forward, and obviously staff coming in the buildings who haven't yet been asked to step up, but this will be a multi-staff level effort. So I wanted to offer my thanks to all of them for their activities. Now, and with that, I don't want to have our speakers who've been very patient in waiting for starting. Would like to get underway. As Teresa mentioned, we have 3 speakers today. Peter Duffy has graciously agreed to join us here in the room from Princeton University. We have 2 folks joining us remotely who get extra stars because one of them is dialing in. Carl is dialing in from California, so it is very early in the morning for him. And Kevin Rosso is joining us from Australia, so it's very late at night for him. So we want to give them our undivided attention and get started with, let me see if I can move this forward. For some reason, it's not advancing, Eric. Can you give me a, thanks. Seems to be hung up. In any case, what we're going to be doing with the session this morning, there we go, is to focus on the molecular level aspects of subsurface contaminants with aspects that would be particularly relevant to this board. And Peter is going to start us off. You have everyone's bio, so I'm not going to go over those here this morning. Each speaker is going to have approximately 20 minutes for their presentation. I'll be nudging them if you start to go over that time. We'd like to move sequentially through the talks without discussion in between, because the main focus that we'd like to concentrate on is actually the discussion at the end, where we've allocated a lot of time for that. We have a lot of collective wisdom in the room, and we'd like all of you to jump on board and contribute to a lively discussion at the end. So with that said, Peter, I'll just ask you to get underway, and I'll use this.
How do I do that? How do I advance it? I don't know how to do it.
Oh, on the button on the...
Oh, on this part.
Yeah.
Okay. I get it. Thanks.
Yeah.
Thanks. Good morning. So just a qualifier, when Teresa asked me to give this overview and also touch these 4 different sections of this conference, I lightheartedly said yes, and within 24 hours I said, how can I do it in 20 minutes? So I will leave important things out, but I hope I touch sort of some major items of interest. So what are the special challenges in soil groundwater pollution? And I want to set it in context with air pollution. When we look at air pollution, and T depends how you want to look at it from an engineering point of view, can be a time constant, for chemists something like a half-life. We're talking about a process that if I get rid of the source, days I can get rid of my contaminants. Surface water, we're talking about months, weeks to months, as long as the sediments are not contaminated. Now, soils and groundwater, we're talking about years to centuries. So it's a very slow process, it's very diffusion limited. So when we look at transport processes and remediation, short time constants, we can address the source. Long processes like groundwater soil, we need to address the source and the pollution, the pollutants by themselves. How extensive is the problem? We can look at regional problems, agricultural, usually at a watershed scale, many square kilometers, usually very low concentrations. There are problems were in Eastern Europe. During Soviet times, they applied lots of fertilizers, phosphate from central ores in Africa that were high in cadmium. So some areas are reasonably high in cadmium, but below toxicity levels. It's site-specific. We're talking about spills, disposals, industrial activity. Most of the times we have high concentrations there exceeding drinking water standards. Here's a little cartoon that I drew about possible exposure pathways. On the left, you see a waste disposal and producing a contaminant plume. It can intersect the drinking water well. We can have septic tanks that contaminate our groundwater. We have atmospheric deposition that provides contaminant loading to soil, and then uptake by plants. Just as an example, when you look at private drinking water wells, about 15% of the US population relies on private drinking water wells. About a quarter of them have at least one compound that exceeds drinking water standards. When we look at the fate of contaminants, there are three aspects that we worry about. One is, can we immobilize them? How are they mobilized? And then what kind of reactions do we have, okay? And in immobilization, usually we talk about sorption or precipitation. Mobilization would be the formation of complexes that mobilize a compound or oxidative dissolution. Reaction, we're talking about mineralization when we have an organic component. Mineralization is when we oxidize it completely or biodegrade a hydrocarbon to CO2 plus water. That can be fast or slow. If it's fast, we don't care. I mean, at the rate at which it decays compared to a transport, it's probably the contaminant is not going to be an issue. It's the slow decaying ones that we care about. Sometimes we have the partial reaction or degradation to stable intermediates, and then change, when we're talking about inorganics, change in chemical speciation. We can go from, I'm going to go that later, arsenate to arsenite, and different transport processes, different toxicity levels, etc. So why do we care about sorption? Very simply, we can describe sorption as sort of a mass of the compound sorbed over the mass of soil divided by the mass of the compound in solution divided by its concentration in solution. When we talk about ionic species, this sorption is a function of the pH in the presence of other compounds. It's rather complex, and we usually describe it by complexation model, surface complexation model. When we talk about low solubility organics, the partitioning, it's a partitioning process, and it's a function of the soil organic fraction. And typically the octanol water partitioning, it's inversely proportional to the solubility, but the octanol water partitioning is a better descriptor. When I look at the partition coefficient, we see here that we can describe it as 0.63 fraction of organic carbon times the octanol water partitioning. What that tells you is that soil organic carbon is about 63% as efficient as octanol as a solvent. So these compounds sorb very strongly into the soil organic fraction. This is a relation developed in the early 80s by Sam Karikov. I mean, there are other relations that look like that. Now, why do we need to quantify sorption? When I look at the velocity of a pollutant, I can derive that, but just looking at this little equation, it's the velocity of water divided by 1 over the partition plus the partition coefficient, the density of soil divided by the porosity of water. Density of soil over porosity of water is essentially something like the concentration of soil, right? So if my partition coefficient is 0, the compound doesn't sorb, the velocity of the pollutant is the same as the velocity of the water. If my partition coefficient is very high, can be the dominant factor, then the velocity of the pollutant is very, very slow compared to the velocity of the water. Now, the same thing happens to chemical reaction. When only the fraction of dissolved component reacts and the sorbed component doesn't react, my bulk reaction rate can be described by the same, as affected by the same partitioning, okay? Biodegradation, usually the bacteria can take up only dissolved components, not what is sorbed or bound strongly. It has to desorb before bacteria can degrade it, so the reaction rate is significantly decreased when the compound binds to the soil phase. Okay. Let's want to move into the next step, and that is soil is really driven by bacteria and bacteria redox conditions. So I can have in my soil a series of different redox reactions and in groundwater. And what we view that is that it goes sequentially. If I have soil organic carbon, I have heterotrophic bacteria that can degrade that soil organic carbon. You get delta G is highest when you use oxygen to degrade organic carbon. Delta G decreases as you go down this ladder. You can view very simplistically as an organism needs the same amount of energy to stay alive, aerobe or sulfate reducer. But so first what they need when they oxidize organic carbon is to get the energy to stay alive, and then the rest they can use for growth. So aerobes will always outcompete organisms in more reducing conditions, especially when our soil organic carbon is limiting. I will certainly go down my redox potential in sort of as shown in the left side, at least that's how we simulate it. There are always some overlaps. In addition to the competition that I mentioned, there are also toxicity issues. Oxygen can be toxic to some organisms that work in the more reducing conditions, etc. But it isn't from a chemistry point of view. When I want to know, so from a chemistry point of view, my bacteria in the soil set the redox condition. And then here's your standard EH/pH diagram. Here I have it for arsenic. I don't know if this works. For arsenic, oxidizing conditions, we have arsenic usually in the soil as arsenate, arsenic 5. We go to more reducing conditions. At equilibrium, it should move to arsenite. Now, it doesn't spontaneously happen, so we typically need some kind of organisms that can reduce the arsenic. So for arsenic, we have some bacteria have an enzyme called an arsenate reductase. They use that to detoxify. And if we have these bacteria present and our redox conditions change from oxidizing to reducing, we change our speciation from arsenate to arsenite. Arsenate sorbs much stronger to iron oxides. Arsenite is much more mobile, but if I go back here and I get into sulfate reducing conditions and produce sulfite, then my arsenite will precipitate as orpiment, and I can remove the arsenic from solution. So it's a very close interplay between the geochemistry and the microbiology. Here is uranium, and I know Carl Stiefel, myself, have worked a lot in uranium. Uranium is interesting. I'll explain it later too. As the pH changes, we go from this uranyl ion, which is positively charged, and to negatively charged. Sorry, this is -2. So positively charged to negatively charged as the pH goes up. My soil is typically soil surface has negative charges, so this uranyl ion will sorb much stronger to my soil matrix. So when I add some carbonate or have carbonate in my groundwater, and the pH is somewhat higher, my uranium, hexavalent uranium doesn't sorb. So usually in the lab, when you want to extract uranium from soil, you use a carbonate solution to extract uranium. Now, when you go from oxidizing to reducing, you go from uranium 6 to uranium 4. Uranium 4 precipitates is insoluble and as a uraninite. And here, we don't have any organism that has a uranium reductase or something like that. But iron-reducing organisms that oxidize carbon they dump the electron on iron 3 are not very selective. So if there's uranium present, they will dump the electron on uranium 6 and convert the uranium 6 to uranium 4, immobilize it in this process. Now, here's a little cartoon that refers to the complexity of soil. When I look at soil, I have different flow pathways. I have some larger pathways. I may have some fractures where water flows quickly and electron acceptors can be delivered quickly. And then I have sort of more pores where I have a little biofilm and I have some diffusion limitations. So at that small scale here, I'm talking about centimeter, I can have large variability in redox conditions. But when I sample, if I put a well in and we get a few mils or half a liter of water, I get the average of my water. So you can look at the composition of what you get in your well water, and it doesn't describe the composition or the processes that are happening in your groundwater. So it's very challenging to often link a sample that you measure to what kind of redox reactions you may have in your bulk solution. Now, we can have direct and indirect bioimmobilization. I mentioned earlier this ion reduction. So we have heterotrophic bacteria, Geobacter, for example, that can oxidize an organic and reduce an amorphous iron phase, and then transfer that electron to uranium-6 to precipitate it as uranium-4. We are working with a fairly newly discovered strain that actually is an autotroph that can oxidize amorphous iron with ammonium as the electron donor. And we have done the same experiments, and we can see that we can, in a lithotrophic environment without the presence of organic carbon, also precipitate uranium-6 as uranium-4. We need ammonium and iron oxides in acidic conditions. Now, we go further down in my redox ladder. If I have sulfate reduction, then I have heterotrophs that oxidize organic carbon. They may use sulfate as the electron acceptor, form sulfide. And then if I have metals present, divalent metals, they typically precipitate out as the metal sulfide, get immobilized. Arsenic can be precipitated as orpiment. So when I look at the mobilization, I have oxidation, reduction, the example of uranium. Uranium can easily be reoxidized again as in the presence of oxygen. So if I immobilize uranium, but oxygen comes back into my groundwater or nitrite, I can reoxidize it fairly quickly. Chromium, for example, I can remove and precipitate. It's very hard to reoxidize chromium. Manganese cannot reoxidize chromium, but otherwise it stays fairly stable. Formation, I alluded to that, formation of different complexes. We can go from something that sorbs very strongly under lower pHs in the absence of carbonates to something that is negatively charged that will actually not sorb at all, a uranyl carbonate complex. And then when we talk about complexation of metals, I mentioned that metals can precipitate with sulfide, but we've done some work in wetlands, highly acidic wetlands, where we have a lot of organic carbon, and the complexation of the organic carbon would override. It was in such an excess, the complexation with sulfide, that the metal stayed in solution. Okay, so you have to look at what kind of other complexation competitions there are to see if what the dominant precipitate is. And Carl Stiefel may allude to that. He's doing a lot of modeling of that kind of these kind of reactions. Quickly, biodegradation of organics. We have 10 to the 8 cells per gram of soil, so bacteria are plentiful, but not always do we have processes occurring. So we can have electron acceptor missing. Sometimes we have hydrocarbon spills. They should be degradable. They're not degradable. They degrade easily aerobically, but diffusion of oxygen is limited. And we can have an electron donor missing. For example, under highly reducing conditions, carbon TET could be dehalogenated but we need an organic carbon as the electron donor for the dehalogenation to occur. Sometimes the concentration is just too low, especially if I have a single pollutant. It doesn't give the bacteria enough energy to grow. Or the concentration may be too high and it's toxic. We have trace nutrients that may be missing. Sometimes a specific bacterium is missing. Dehalogenation, the groundwater remediation folks have this dehalogenated rhodococcus, so they grow it, they inject into the ground, and you can dehalogenate compounds fairly quickly. And sometimes, let's say trichloroethylene, for example, in the oxidation of methane to methanol, the first step is done by an enzyme, a methane monooxygenase, which is not very specific, and it can epoxidize you with trichloroethylene. Okay? This trichloroethylene has half-life of a few seconds and then decays fairly quickly. So we have to see what may be missing and why is something reacting or why not. Okay? Now, moving on to the next little topic, roots. If we're talking about soils, roots are quite complex. They release root exudates or siderophores. Root turnover provides a carbon and nitrogen source that will affect the soil chemistry. Plants alter the water flux as plants lose water and in the unsaturated soil, it will dry out. It will change your redox conditions. In saturated soils, it will make the water flow through the plant. Let's say wetland plants, for example. They release oxygen into the pore water. Plant tissue has to stay aerobic, so wetland plants have adapted to pump oxygen into the root system, and roots are leaky. So in the surrounding of wetland roots, you have iron plaques forming as the plant pulls water for transpiration, and there's, let's say, iron 2 in solution. It comes in contact with the oxygen that diffuses out, and you have these iron plaque formations. Here's some pictures. This is something I took at a field site where you have these iron oxides, and these are experiments with it in the lab, where you can very clearly see how around the root we have these iron oxides being formed. That affects your sorption, that affects possible reactions that you may have in soil, etc. So we have done, for example, mesocosm studies with uranium, where we did Zane's analysis, and I think Kevin, right, will talk about that after me, where you can look at the speciation of uranium in these precipitates. And one thing what we thought is that because we have so much iron that we would have reduction of uranium and immobilize it as uranium-4. But actually we were pulling the uranium towards the root and then encapsulating it in iron oxides. And the advantage of that, or the outcome, is that wetlands periodically dry, and we had assumed that when a wetland dry, it will release a lot of uranium. But because it was encapsulated in the iron oxide stayed stable as the wetland dries, and so the uranium stayed stable. When we looked at sulfur species, for example, we saw that when you augment mesocosm with higher levels of sulfate, we push the system towards more sulfate reduction. That in turn stimulates arsenic reducers, and we saw that we converted much more arsenate to arsenite, and the arsenite is more mobile, so we would see that we saw about 30 times more arsenic in roots, and the decrease in the leaves as the sulfate changed. So what it shows, the soil chemistry and plant uptake of a contaminant is very, very complex. You have to look at how the redox conditions change, what the competition is between different molecules and plant uptake. Here's an example of an emerging contaminant, that molecule that in the remediation industry everybody's talking about right now, the polyfluoroalkyl compounds. They make products resistant to water. They have been used quite a lot. They have also used for fire suppressants, and especially by near airfields, these foams have been applied widely. Turns out now that PFAs are very stable in the environment. They have been found in blood samples of the general population, animals. They're toxic to laboratory animals, and they're suspect of causing cancer. Concentrations have been 10 to the 4 to 10 to the 5th part per trillion near airfields, typically. They have a reasonably high solubility. This is milligrams per liter compared to the toxicity levels. KOW puts them roughly in the range where tetrachloroethylene is. They sorb but are reasonably mobile. And the challenge then is, as we learn more and more, this was EPA's recommended health standard for 2002, 150 parts per trillion. It's today 0.07. You go to some states, Vermont, 0.02. So as we learn more and more of some compound that we thought was a great product, it becomes a challenge when it enters in soil and becomes a groundwater contaminant. Let me go to the large scale, and I'm focusing on nitrogen, for example. We probably doubled all of you know that, the amount of nitrogen that is being fixed since the Haber-Bosch process was invented. EPA's limit on nitrate, for example, in drinking water is 10 milligrams per liter. Here's a map of the US. Many locations exceed these nitrate drinking water standards. The problem is, in addition to health issues, oceans and estuaries are nitrogen limited. As we export more nitrogen, we see problems like the dead zone in the Gulf of Mexico. You see pictures by China with huge amounts of eutrophication in the coast due to excess nitrogen. I'm working a lot with the Chinese Minister of the Environment. It's the only place where I've seen rivers that have more ammonium than nitrate. The amount of ammonium that they're putting on the land is just huge. Very quickly, just sort of nitrogen, we fix nitrogen, ammonium, it gets incorporated into plants, decays. These processes, nitrification, ammonium gets oxidized to nitrate, are aerobic. These processes, denitrification, are anaerobic. Nitrate is used as an electron acceptor in the degradation of organic carbon. So when we want to cycle nitrogen back, the fixed nitrogen to nitrogen gas, we need this combination of aerobic and anaerobic processes. So here are some of the challenges. This is some work we've done fairly recently for the Susquehanna. What this shows is the deviation of nitrogen exported by this Susquehanna as a function of the deviation of climate. The previous year, the previous 2 years, the previous 3 years. So here, for example, a 4-year season. So here I'm looking at a normal year where the previous 4 years were dry or the previous 4 years were wet. Okay? And this is a deviation of the nitrogen export of the Susquehanna. So what we see is that there is a significant impact on how much nitrogen is exported depending on climate variability. When our soil is dry, we accumulate more nitrogen. We can oxidize more ammonium to nitrite, but the nitrite is less mobile. When the soil is wet, we have the opposite effect. And when we do modeling at that scale, we do some very simplistic and to me highly unsatisfying sort of relationships where this is a multiplicative factor that we apply to the ammonium oxidation rate as a function of the soil moisture. So we're saying essentially that when my soil is dry, bacteria need water, they live in a wet environment, the maximum my nitrification can occur is at 20% of its maximum potential. As it gets wet, my nitrification starts increasing up to a certain water content, and at some water content, 60% or so, it depends on the soil, I have enough water blocking the diffusion of oxygen into the soil so that my nitrifiers become oxygen limited and my reactions start to decrease. Denitrifiers are the opposite. They're the anaerobic organisms, and they don't work while there's oxygen, but at 60% water content, I start to block in some niches of the soil diffusion of oxygen, and I start to see denitrification occurring, and then once I get to 80–90%, it's occurring at full speed. Okay? Now, all of us that look at a molecular level find this utterly discomforting. I mean, we do understand the processes at a very small scale, and then washing this sort of under the rug is somewhat difficult. I am running out of time, so very quickly, let me skip this slide and just go to the last one, which I was debating to put up. So what are major advances or gaps remaining? It's my personal bias. We certainly can reliably predict abiotic dynamics of most chemical species, and Couch people will sort of describe very nicely how they do this modeling. There are many new developments in analytical imaging methods, veins, atomic microscopy, that give you details of speciation of different elements at the soil matrix. We can look at in details at the characterization of soil, iron phases that you have in the soil, etc. There are many advances in understanding biodegradation. We know what kind of gene we're looking for and what kind of reactions are possible. It's still challenging when we have lots of organics present to see what will be dominant and what kind of reaction are we going to see. We do understand physical transport limitations. I can draw you a picture and tell you exactly what will happen. But once you stand on the surface, it's your guess what kind of aggregates you have, where do you have diffusion limitations, etc. And then I put it as sort of as a humorous slide, but I said surprisingly, we still get surprised when new molecules turn out to be a soil groundwater contamination problem. I think we need to do a much better job when we look at specific molecules that are meant to be applied widely, like firefighting foam. What are the implications? We know that we are applying it on purpose on an acre of fire. It's going to go into the groundwater. And what are the implications? Ideally, we want a molecule then that is not very stable, so that it will decay naturally. And that's, I think I'm out of my time, and thank you.
Thank you very much, Peter. I'm going to take my moderator's prerogative and not entertain any questions now so that we can keep moving. If we're ready, we'd like to move on to Kevin Rosso's presentation. Kevin, are you there?
I am. Can you hear me?
Fabulous. No, you're loud and clear. Were you able to hear Peter's presentation as well?
Yeah, very well. Thank you.
Fantastic. Well, I think I'll just turn it over to you then. I don't have an electronic velvet hook to pull you off at the end of your 20 minutes. So just do your best to stick to the time, and we'll see how it all comes out. Thanks very much for joining us from Australia. Please go ahead.
Okay, thank you. I'm trying to share my screen now, but it's disabled by the host. Okay.
I think they're working on that, so you should see it in a minute.
Okay. Can you see that?
Yeah, we can see that, and can you see us in the room and so forth? Yes. There you go.
Okay, amazing, it works. Just a second. This should do it. Yeah. Okay, so I'd just like to take off from where Peter did a very good job overviewing some of the major issues that I guess we deal with when we're thinking about contaminant transport in the subsurface. Charge, as I understood it, was to show you one or two examples where we use molecular scale information to try and help decision making in terms of predictive modeling. And so what to do was try and feature two examples in this 20-minute talk, roughly 10 minutes apiece. First on trying to understand the reactive transport of technetium-99 at Hanford. The Hanford site is kind of emblematically represented by the black and white images of tanks up in the upper left. Also then the second example to talk about 137 cesium at Fukushima, conceptually illustrated by the map of its distribution through the ocean in the upper right. So those are my examples, and I will try and be efficient and get through basic ideas with regards to those two systems. The outlining key messages. So the subsurface environment, I hope you saw in Peter's talk, is chemically and physically complex. And I would say in rare cases can contaminant reactive transport models predictive, even with modern day approaches and technologies and knowledge. Molecular scale techniques are at the forefront of robust model development. And I will illustrate those in the two examples I mentioned. The Hanford case for Techno 99, synchrotron light sources and X-ray absorption spectroscopies have been very useful. For the cesium problem at Fukushima, I'm going to talk about a case where experiments really are not so useful, and molecular simulation comes in very handy. Just as a philosophical statement, though, I would say that striking the best balance between detailed chemical process understanding and useful working models remains subject to practical considerations such as time, money, and the specific need. So this is a map of DOE's Hanford site, which is one of the biggest contamination problems in the world, definitely in the US. It's 586 square miles of Washington State in the south central region. During World War II, it produced 67 metric tons of plutonium for weapons. And back in that day, there was not much concern for the environment. So as they processed this plutonium through vast quantities of various types of extraction and separations technologies, with a lot of waste, most of which has leaked into the ground. A lot of it is still stored today in 177 huge underground tanks, 67 of which have leaked. And there are incredibly hazardous radionuclides in the surface at Hanford that DOE cares about and is being mandated to clean up. That also equates now to what has been estimated to be about 200 square miles of contaminated groundwater in the Hanford territory, which is migrating to the Columbia River, which is shown in the map. It's a major river in the Pacific Northwest that also runs by Portland. This is to give you a feel of kind of the then and now of the Hanford site. By and large, all the activities on the Hanford site are decommissioning, deconstruction, brownfielding, and waste plume management. The Columbia River there, shown in the lower left, is the major driver for remediation decisions. You know, when you go into the ground and you want to pump and treat, or let's say you want to scoop out contaminated soil and sediment, you do worry about remobilization or enhancing the transport of a contaminant into that water. And that's, by and large, what goes on at the Hanford site today is cleanup activities with major concern of the Columbia River. Among the various radionuclides that have been leaked into the ground, the ones that they worry about the most are the ones that are the most mobile, of course, and out that, and I believe Peter said this, the ones that often are the most mobile are ions, because surfaces of geomedia tend to be negatively charged. Soils and sediments at the Hanford site are basaltic provenance, very alkaline. You do end up with high pH groundwater buffering. So there are species like chromate, which is an oxyanion. There are species such as technetium that are oxyanions, and they tend not to stick to anything in the ground, and they move quite fast. So technetium-99 mobility in this vadose zone at Hanford is very poorly predictable. It's a very thick vadose zone. It's an arid climate, so hitting the groundwater, sometimes you have to travel hundreds of meters. Major concern because it's a beta emitter, it's going to be around a long time, obviously toxic and carcinogenic. They know roughly how much of technetium-99 has been disposed into the subsurface. That's plus when you're trying to figure out how you're going to try and get it out. Like the uranium case that Peter talked about, it has two major oxidation states that really dictate its aqueous solubility. Toxic environment, it's technetium 7+, which is the oxyanion I mentioned that is highly soluble and mobile. If you can get it into a reducing environment, it will convert to technetium 4, and it will drop out as TCO2, which is sparingly soluble. And that is one reductive immobilization strategy to try and reduce technetium from 7 to 4. So yeah, the major issue with the Hanford subsurface and technetium is to figure out whether or not this reaction basically will go spontaneously or not, as the technetium in the oxyanion state makes its way to depth. And so the question is, can we get it to reduce in the Hanford subsurface naturally? Do you get deep enough so that oxygen supply is limited to allow the system to evolve towards more reducing conditions, which can supply electrons to reduce technetium? We have done some work looking at these Hanford sediments, and this is kind of what they look like. And if you look at them with Zanes, which Peter mentioned, and you map the particulates in that sediment body of the Hanford Formation, you find hotspots of iron, shown in red in that X-ray fluorescence map. There's another picture based on synchrotron analyses showing iron and titanium co-associated in the mineralogy of Hanford sediments. And the reason for that is basaltic provenance in that region, which has led to is the soil term for these sediments, is rich in iron, it's rich in magnesium, and it's even got as much iron as shown in the upper right, which are basically pure magnetite crystals that are detrital in nature that have weathered out of the original basalt and are still preserved to this day. That's an Fe3O4 phase. It's magnetite. Many of us have heard of it. It's magnetic. It's got in it. The question is there enough of this material, and is it reactive enough to supply the electrons to reduce technetium from 7 to 4? So Fe3O4, if you break down that composition geometry, it's got a component of iron 2, ferrous iron. That's the electron source that we're interested in. Is there enough of it? Is it accessible, and is it reactive enough to convert technetium from 7 to 4? It's a complicated question at the molecular scale because these magnetites have a high concentration of titanium. Titanium goes in as a 4+ cation into the lattice. So the more titanium you get replacing iron 3+, the more you charge balance that structure by converting iron 3+ to 2+. In other words, higher titanium, more ferrous iron concentration, therefore nominally more reducing power. So one of the things that we've done quite a bit of work on is to try and develop model systems that we can measure in the laboratory to see if this reaction should really go. So in the upper right are synthetic titanium-doped magnetite nanoparticles that we use for reactivity studies with pertechnetate. And this is just a look at how fast that material will actually react with technetium-7. These that show the concentration of pertechnetate dropping out of solution over time, on the time scale of minutes, in fact. X is the quantity of titanium, which is the proximate quantity for how much ferrous iron is in this material. So nominally, this reaction, these data suggest that this reaction is going forward. But how does this really happen is what we wanted to know at the molecular scale. And so we went to the ALS, Advanced Light Source at Berkeley, which is a synchrotron. That is the ring. Electrons are circulating around that ring, and out of the exterior portions of the ring, of course, are the end stations where we use the X-rays. So the really bright, coherent X-rays that you can tune across a range of energies and sample its ability to be absorbed by your sample in a chemical specific way. So you hit your sample basically with the X-rays, electrons come off. If you do that in this electron yield mode way, it's very sensitive. You're only sampling the upper 5 nanometers of the surface. Nanoparticle model system. Because it's magnetic, we can take advantage of a relatively cool new technique called circular dichroism. If you hit your sample with circularly polarized X-rays, and you do it with a magnetic field applied to your sample, and you reverse the polarity of the magnetic field, basically measure 2 X-ray absorption spectrums at inverse magnetic field. You become selective for different states based on their spin in the structure. So this is a surface-sensitive molecular tool for, say, iron that is specific not only to its valence, but also things like its magnetism and its local coordination. Look at the end station that we use to do X-ray S and XMCD. This is what it looks like if you look at a magnetite sample, XAS and XMCD. The peak here, the larger peak, the L3 edge of iron, you can see differences in the shape of that peak between the red and the black, and those are the opposite field polarities. Like L2, you can also see magnetic field dependent features. So if you subtract those 2 spectra, you get an XMCD spectrum that looks like this, and basically just goes to show that among the 4 types of iron sites that exist in magnetite sublattice, we can basically see them all. We can differentiate them in terms of their valence and also whether they're in a tetrahedrally coordinated site or an octahedrally coordinated site. The bottom line is this technique was very useful for quantifying the action of the surface with pertechnetate. And this is just one example that I'll show where you can basically quantify the loss of the octahedral iron 2, shown in the lower left, and that is quantitatively related on an electron and mass balanced level with the amount of technetium that has gone from 7+ to 4+. So with models or with approaches like this, we can develop very detailed molecular models about how these kinds of transformations occur at a, of say, these magnetite particles at the Hanford site. This is just a quick overview of all the things that we were able to learn on the basis of the synchrotron approaches, such as electrons are redistributed at the particle surface, how that surface responds to changes in pH, how that surface then responds when it is contacted with an aqueous solution bearing mobile C7. So the reduction process is quantitative. We were able to show basically that the solids evolve in a specific fashion, and that something about the propensity of these Hanford magnetites to reduce the inventory of technetium-99 at the Hanford site. The answer to the question, more or less, that we provided to decision makers was yes, this should go, and in fact, there's enough titanomagnetite in the Hanford subsurface conceptually to reduce the entire inventory of technetium. Whether it happens before it hits groundwater is an unknown, but we can tell them approximately how much Tech-99 can be immobilized as it contacts this phase, as it percolates down through the sediments, and at what rate. Let's move on to the second example, and I hope I'm doing okay on time. I did want to mention the Fukushima problem in Japan, which we have done some work on, in basically trying to understand where the all the cesium that was emitted aerially from that nuclear accident, where that ended up in the world and where it's ending up in Japanese soils. I'm sure you all remember this incident. It's still fairly recent, but pretty devastating tsunami hit the region, which knocked out the all electrical and backup power to the nuclear power plant. A major meltdown and explosive failure of 3 of the 4 nuclear reactors. This obviously was a very bad accident that released lots of fission products atmospherically into the region. And this is a map of of basically the first few months, I believe, of what those emissions look like, and basically where these cesium-137 and cesium-134 radionuclides were distributed in the Fukushima region. Fast forwarding to present day, the Japanese have been remarkably efficient at scooping up about the top 3 meters of soil in every accessible area that has been contaminated. And they have soil bags in temporary storage facilities that look basically like this. These are awaiting final disposition. The scale of the accumulated waste soil is massive, and deciding what to do with it, how to process or permanently store it, and possibly reuse some of the material is what they're dealing with today. So one of the questions that they're really interested in is what is the ultimate fate of the cesium in these soils? Okay. Bottom line here, I know Peter talked a lot about organics, and obviously in soil you've got a lot of organics, you've got a lot of tree litter, you've got a lot of things of that nature. But ultimately we know that cesium will eventually like to migrate into these very selective sites of clay minerals, frayed edge sites. It's an ion exchange reaction. The cesium basically will kick out a native alkali cation such as potassium, preferentially, and strongly bind into these edge sites of these clays. And this is already happening at the Fukushima site. You can go out into still contaminated soils. You sample that, you look in the clays, and you can see the hotspots of cesium associated with the clay particles. So this exchange process is thought to be irreversible and permanent. And the question is it really? The half-life of cesium is about 30 years. And so it would take a long time to really ultimately learn that or try and do that experiment in the laboratory. So we did some molecular simulations on this particular problem. We first showed that we can put cesium into this model clay minerals, similar to those in the Fukushima soil, in a computer and see the same phenomenology. And that is that cesium will preferentially replace potassium at edge sites that are open to a certain distance, frayed edge sites. And we can actually see that the calculation agrees fairly well with the experiment. The question is about this long-term retention, and that is, how long will the cesium, which is a radionuclide and it's emitting particles, how long will it be stable in these clays? Is it permanent for 50 years, or do we have to worry about absorption from these materials over time? These are TEM images that show that if you concentrate cesium in solution and you expose these clay minerals to that concentrated cesium solution, that cesium will preferentially segregate the interlayers and form concentrated domains. And the reason that is interesting is because if the cesium is causing radiolytic damage, let's say to the crystal lattice, if you damage one of those layers, then you could be risking delamination and re-release of the residual parent isotope. So the question is this process happening, and is it relevant to the future of Fukushima soil? And without going into the details for the interest of time, let's just say that it's very amenable to density functional theory, quantum mechanical calculations. So there are methods out there where you can basically compute the energy of a defect in a solid. The defect, let's say, being the cesium. You can even easily change the cesium's identity to its transmuted daughter isotope, which in this case is barium. Barium has a different charge. It wants to be a 2+ cation. Cesium wants to be a 1+ cation. That obviously makes a large energy contribution, destabilization of that particular binding site, to the tune of about 400 kilojoules per mole. So the question is, if that process of, let's say, the cesium is being substituted into the lattice, it's transmuting over time to barium 2+, is there a compensation pathway in the solid that will allow the system to relax to a isoenergetic or stable structure, let's say, without having to delaminate and release the cesium into the back into the environment. And the question is, well, the answer is really no. Once that transmutation process begins, there is a strong driving force for the cesium that is residual basically to kick out back into solution, preferentially even to any residual potassium that actually might be in there. Calculations basically give us an idea that while cesium exchange into these sites is strongly favorable, thermodynamically favorable on the onset, decadal timescales, you actually have to build a conceptual model that is basically absorption, re-release, and absorption in these materials to truly understand and forecast the evolution of that system. So that's an example where experiments would be very difficult to actually have developed that information, and molecular simulation came in very handy to provide some insight that would be useful for decision making. I'm just going to go ahead and wrap it up here with just some high-level observations. I would say that molecular scale experiment and theoretical techniques are at the forefront of robust reactive transport model development. Such techniques have provided useful input for decision making. It's really then comes down to a tug of war of circumstances and stakeholders, and basically the specific need for the contaminant forecasting. Whether or not you would go so far as to invest time, energy, and on the molecular scale to really build a robust model. But these robust models basically, we have line of sight to them, and molecular scale techniques are at our disposal to help make models as strong as possible. So I think with that, I'm just going to wrap it up. I hope I did okay on time.
Thank you very much, Kevin. Absolutely fascinating. Thanks very much. And again, I'm going to take my prerogative and ask you to keep those questions in mind for later. We'd like to move then directly on to Carl Stiefel's presentation. Carl, are you able to hear us?
Yes, I can hear you. Can you hear me now?
You are loud and clear, yes. And thank you, Carl. In the reverse sense, Kevin was very late. You were very early. We're appreciative that you're joining us from California. And so I think they're firing up your presentation there. Can you see that?
I can, yeah.
Fabulous. Why don't you get underway then, please?
Okay. Yeah, I'm going to just let you guys advance the slides. I'll try and remember to mention it, but I'm going to give a brief overview on bridging the molecular, pore, and plume scales in contaminant transport modeling. And as you'll see, a lot of this is driven by the high-resolution molecular characterization, some of which Kevin Rosso was talking about, but that'll come through as a theme, I think. So next slide. So just briefly, acknowledgements. Most of our work has been funded by the Department of Energy Office of Science, actually different programs within so-called BES and BER. Definitely Office of Science has taken the lead in sort of driving this move towards multi-scale models, but also multi-scale characterization, although we have some past funding that are more the applications area. Next slide. Next slide. So when we look at modeling here, and you could prepare an equivalent here perhaps for characterization. In fact, I had one of those. I think it got pushed down to the bottom of my presentation, but this one works pretty well. It's basically when you start to look at the scales of modeling, there's quite a range that's been considered, going from molecular scale, pore scale modeling, very active now in certain parts of the community, up through plume scale. Plume scale we probably did more of, say, in the past. And now the new big drive also, in addition to molecular, is actually to take it beyond plume scale to what we call a watershed scale, where you start to look at the whole range of terrestrial processes, including plants, exchange or interaction with the atmosphere, but also hydrologically, you're talking about interactions between surface water, say rivers, streams, and groundwater. And again, Fukushima is a classic example of how that all plays out. This is the range of scales, but the thing is that when you look at it mostly, not entirely, we're considering these individual scales without coupling them between, say, molecular pore. So certainly the challenge of the next 5, 10, probably 20 years is to consider more formal, explicit coupling between scales so that the larger systems, say the plume scale, which is really what we're interested in the end, we don't care that much maybe about in isolation a centimeter patch of ground. We want to get the overall watershed or plume scale, how it's influenced by molecular to pore scale processes. Next slide. So just beginning with a nanometer scale, which would include molecular. Next slide. Really what we're talking about here is molecular information that might play out in both molecular models, but also we try to capture them in larger scales, so-called continuum models. I'll briefly talk about that, but the real driver here is this molecular electrical double layer. And Peter Jaffe already talked about this. You know, there's a tendency with soils and fine low permeability materials that they tend to get ignored, because when you look at the total, say, Darcy flux through an aquifer, it's so much dominated by the permeable conductive pathways like sand. But in fact, contaminants in particular reside in these fine-grained, shaly, often clay-rich materials. Either the contaminants are there or they're acting as aquicludes, barriers to migration. So we really can no longer ignore these shale or clay-rich zones. But the issue with electrical double layer is that a clay is always basically negatively charged surface that attracts cations close to the surface. And it turns out that if you've got a fine enough, low enough permeability, a lot of the transport is actually going through these electrical double layers, or EDLs. We no longer have necessarily huge amounts of so-called bulk water, electrically neutral water, unless a big fracture develops. And in fact, you can compress these shale or clay layers so closely that the electrical double layers, as you see in the right there, actually overlap. And we never, within those interpore space, you never actually get back to bulk water, electrical potential equal to zero. You actually have overlapping. In fact, that's the source of, say, osmotic pressure, osmotic swelling in these systems. So this is a challenge to capture the electrical double layer. Next slide. And one way to do it, well, one way to do is molecular. I'll come back to that briefly. With molecular dynamics now maturing to the point where we almost use it as a gold standard base case for describing reality. In combination, say, with synchrotron, that's the so-called reality. I'll come back to that next slide, but we can do quite a bit with these so-called continuum models, but we need to modify them or use something different than just good old Darcy's law and Fick's law for diffusion. So what we tend to use now in electrically, in solutions, solutions with a lot of ions, charged ions, we use the Nernst-Bloch equation, where J is the flux. The term on the left is the classic Fickian diffusion that would be used in most groundwater models. But then we've also got the second term, which is either called electrochemical migration or the diffusion potential. It's associated with the fact that ions try to move at different rates. So if the hydrogen ion is moving 5 times faster than the chloride ion, you get electrical imbalance, generates a counterflux that basically slows the hydrogen down, speeds the chloride up. So this is the kind of thing, if we want to accurately model contaminant migration under diffusion control conditions, we have to include this second term there. And you can even have a third term in the case where you got strong gradients in ionic strength. But we can also combine that with the classic Poisson-Boltzmann equation, which is giving you the Laplacian of the electrical potential is related to the charge density at any one point. So starting at, say, the charged surface, you've got a charged media, which then decays back towards, as I showed earlier, back towards electrically neutral water. Next slide. So we've done at least some comparison of molecular dynamics and Poisson-Boltzmann. There's maybe a tendency to think that the Poisson-Boltzmann being a continuum model doesn't work all the time. But comparing it to, again, what I call the gold standard MD, you can see in the lower panel that if you do the Poisson-Boltzmann correctly, at least for the, say, monovalent cation, sodium chloride, you get pretty reasonable agreement in the positions of where the various anions and cations reside. It becomes trickier when you got large hydrated molecules, because then there's this so-called steric effect. There's only so much space to cram them in next to the charged clay particle. Also a problem with divalent cations. So there's definitely some issues with the Poisson-Boltzmann. But you can see in the upper right, for example, this is a simulation that shows the so-called anion exclusion effect in clays, with chloride very much absent in those intralamellar spaces because those are all negatively charged mineral surfaces. And you see the accumulation of sodium in those zones, both of them then connected to the bulk water zone along the middle there. So, but this is a case where it looks like the Poisson-Boltzmann, even though it's not perfect, works fairly well in comparison to molecular dynamics. Next slide. The other thing we do is, because we don't always want to solve the Poisson-Boltzmann equation with a, say, 1 nanometer or half nanometer grid spacing. You know, you get, if your electrical double layer is 4 to 8 nanometers wide, you're going to use up a lot of grid cells just to resolve that single electrical double layer. So we use the so-called mean electrostatic potential approach, where we basically equate the chemical potential of a species in the bulk water with that in the EDL, and then write a Boltzmann expression. Here, instead of an exponential, a simple decaying Poisson, not simple, a Poisson-Boltzmann type expression, we use the mean electrostatic potential, and we basically develop what we call a double continuum model, one for bulk water, one for the electrical double layer, with the electrical double layer defined in terms of that mean or average electrostatic potential. And then we do basically a solve for the mean electrical potential by solving a charge balance equation. So very simple in principle, charged mineral surface potentially modified by sorption, balanced by electrical double layer. And that's the way we can handle this. Again, the electrical double layer, because it's important for transport, cannot be completely ignored as to its particular properties. Next slide. So this is a case where we take that mean electrostatic potential, very interesting, cool experiment that was run actually by the Swiss Glaus et al. In 2013. They took a diffusion cell somewhat like the one shown on the left there, where you basically circulate water, so you maintain constant concentration boundary conditions on either side of the diffusion cell. They put a gradient there between half molar sodium perchlorate and 0.1 molar sodium perchlorate on either side. So a concentration gradient. But then the clever part here again is they spiked the two reservoirs with the exact same concentration of the isotope sodium-22. Now, Fick's law applied. There's no gradient in sodium-22. There should be no diffusion at all. Nothing should happen if Fick's law applied. But actually, when you look at the data and also use that mean electrostatic model, you see uphill and downhill diffusion of the sodium-22 as it gets dragged along by these other charged ions that are moving within that gradient. So this is a case, usually I have a big thing that shows Fick's law crashing and burning. But this is a case where you can't use a Fick's law in a straightforward way to capture mobility. In this case, sodium-22, but the same would apply to a contaminant. Next slide. And just to show you that that was for the case of, say, a bentonite backfill in nuclear waste, which is probably the most common application for this whole problem of anion exclusion. In other words, if you're going to have a safe nuclear waste repository, you got to understand that behavior for clays, but it's also important for so-called clay rocks or shales. Here in the left, upper left, is more or less garden variety shale, the Opalinus clay in Switzerland, where they ran a diffusion test, basically put a cocktail in a borehole into the Opalinus clay and watched the various ions and solutes diffuse out of it. And what you see over there on the right is that basically comparing with a non-charged tracer, the iodide, the anion, is diffusing out basically at, say, 50% of the rate of the uncharged species. So again, we see that in basically garden variety shales or clay-rich rocks, there's a big effect for anion exclusion. And the same would apply for any negatively charged contaminant like uranium carbonate species that Peter Jaffe was talking about earlier. Next slide. So jumping now to the pore scale, that was some continuum modeling, but basically always motivated by the molecular scale, say electrical double layer. The pore scale, next slide. Here we've got this contrast. I'm not really contrasting it with the molecular, more with a larger continuum, and some people like to call it the so-called Darcy scale, the upscaled average porosity, where you define, say, a permeability of the bulk media. But when you look at it, pore scale models, you're actually resolving solid, gas, and liquid interfaces. And within the pore, you can get gradients in concentration reaction rate that develop. For example, here, shown in Lee and Stiefel 2008, and Yang was the other co-author on there, you see actually flow down a reactive calcite-lined cylinder. Where you see is all the reactions occurring at the wall of the pore, and then the middle of the pore with this Poiseuille flow profile basically is much more dilute. So you're capturing gradients. This contrasts with continuum models where basically you've got a bunch of grains all within some representative elementary volume. They all coexist there, but it's treated as if the reactions, here talking geochemistry, are taking place throughout the control volume. And you're basically assuming the fluid phase is well mixed, so there's no gradient. So this is a big contrast. Next slide. And in fact, I won't belabor this, but here you can talk about the pore to continuum scale and flow. The classic description would be Navier-Stokes, which would produce that Poiseuille flow profile, versus, say, the Darcy scale, where you just use this bulk permeability parameter. And in fact, Darcy doesn't capture this parabolic velocity profile that the Navier-Stokes would. But you also can do it in terms of reaction down at the bottom there. At the pore scale, you basically put in reactions at the mineral surface, if it's a mineral water reaction, and then you explicitly put in the diffusion control back from that surface out to the bulk water. This again contrasts with our continuum models for reactivity, where we just use this lump parameter surface area that might have some physical basis, but also has wrapped into it all of the local diffusion controlled transport effects within the porous media. Next slide. So we've done a lot of work on this, mainly in Energy Frontier Research Center, trying to develop a sort of a workflow that goes all the way from characterization to pore scale modeling. We actually set up in the upper left there a capillary tube experiment, a fancy version of a column experiment, except that with my eyesight, I can barely even see the experiment, a good reason for me to stay out of the lab. But then we take that experiment, which is we're gonna pump reactive fluid through there and collect effluent, just like we would with a normal column experiment. We also do microtomography at the ALS to capture the pore structure. We render that digitally for the purposes of simulation in a capillary tube. So that upper right corner is actually completely digital image of the calcite grains there. You can see the rhombic cleavage even. It's a completely digital image showing the interface between the solid and the liquid. So that's a computer image reprocessed in 3D. And then we actually run the pore scale reactive transport. I think the one below was 2-micron resolution, one of the largest reactive transport simulations ever run. 3 billion degrees of freedom. You need a big petascale and approaching exascale computer to even run that. But it captures then all of these gradients in pH, the diffusion control comes out of it automatically. Just to make sure we're actually doing it right, then we compare it with the effluent chemistry, which is already the so-called volume averaged, flux-weighted average of all of those pores leaving the system. We see how well we're doing in that case. So this is the kind of workflow between characterization, experiments, and modeling that we're trying to follow. The next slide. And this is the kind, as I mentioned, really this is becoming an exascale computing project. We have one through the exascale computing program. There's Corey over there on the upper left, was number 5 fastest in the world, might have dropped to number 7 now. And then we also considering multi-scale systems in the upper right, ranging from the pore scale, in this case not quite molecular, but all the way up to the reservoir scale. And then down below, just an example of a fracture through dolomite that's been infiltrated by CO2-rich fluid, CO2 being a weak acid, it's going to dissolve it out. It shows the chemical erosion of the pillars that are holding that fracture open over time. The one up top, the initial, the one below after 18 hours, where some of the pillars have actually been eroded. Next slide. So then the plume scale pretty much end up here. Next slide. In fact, I'm coming back to Hanford, which fortunately Kevin Rosso summarized already. But this is a case where we look at how this molecular information actually affects the plume scale behavior. By far in the upper left here, the worst tank that I recall at Hanford was this SX-108 tank, which when they sampled under, it just blew all their detectors for cesium-137 off scale. And part of the problem was this was the case where the classic linear distribution coefficient models, KD models, failed after they got through the initial thing of just blaming the modelers for everything. They realized that there was some conceptual issues and they needed new conceptual models for cesium transport. And basically what it came down to is 2 things. One is that there were 2 different sites for the cesium. One was the frayed edge sites that Kevin already showed a nice picture of, which very strongly sorbs the cesium, but then there's at least some cesium also on the surface of expansible clays. So as shown by the binary exchange data from Zachar et al. In 2002, you're basically conditional selectivity coefficient, which is a cation exchange concept, but it's like an equilibrium constant. You can see that the data, as you load the thing up with more and more cesium, the data shows that you're switching from one selectivity coefficient, very strong, that's the so-called frayed edge site, to a lower, although still substantial selectivity coefficient. So we got 2 sites. But again, what we need here is more like a cation or ion exchange model to capture the competition. That's shown in the next slide. Basically, if you look in the upper left, this plot of the cesium KD in Hanford sediments, you see that the KD is a function of both cesium. The more you load it, the more you run out of those strong frayed edge sites and you have to use up those planar sites, but also competing with sodium. In other words, if the sodium concentration is high enough, it starts to compete with the cesium. And this is non-trivial because these tanks were basically nitric acid plus sodium chloride, and it forms sodium nitrate. Very strong, say 10 molar, 15 molar sodium nitrate, which then competes with the cesium. So when you look at the thing, you run the model based on the experiments, you develop a cation exchange model. You see, okay, nitrate being non-reactive moves down almost all the way through the system. Cesium at 1 molar moves, say, the scale is not really shown here, but a short distance. But you increase it to 5 molar sodium nitrate, the cesium starts to move much farther through the system. And in that upper panel on the right there, you see that it starts to explain why cesium moved as much as 30 feet below the surface, way, way further than was supposed to be with the classical KD models. The good thing here is that, and this will be told DOE, I don't know that they believe this, but that we saved DOE $100 million to $200 million in cleanup fees, because we basically said, if you no longer have that high concentration sodium nitrate pulse leaking from the tank, and you go back to more normal groundwater, soil water, you're basically not going to move that cesium any further because it's stuck on those frayed edge sites. In other words, if you don't have that 5 to 10 molar sodium nitrate, you're not going to have a cesium migration problem significantly. Next slide. So this comes back to, I won't say much of it, but the Fukushima that Kevin also talked about here. And what we were trying to do there is watershed scale modeling of the individual compartments as affected by, say, in particular, vegetation. So forest soils, water bodies, groundwater systems, but also forested versus farmland. And what we're developing was high resolution overland flow models, basically coupled surface, subsurface, water flow models predict erosion of cesium-137. In other words, if cesium is totally sorbed on these frayed edge sites, then the contaminant migration problem becomes one of predicting erosion. And in the case of erosion, yeah, you can use the universal soil loss equation, but our approach was to use high resolution modeling where we basically predict the amount of overland flow as a function of, say, whatever monsoon tempest comes through there. And we're able to predict that accurately. We get a better description of how much cesium via erosion is actually moving down through these forested catchments into the regional water systems. Next slide. And this takes us back up to the overall, again, we've got an exascale computing problem here. This is an example from East River in Colorado of a high resolution image of a watershed. You can take it all the way from the pore scale, like in the upper right there, to the so-called nested hierarchical scale terrestrial modeling shown on the lower right there. You've got a big watershed that's, say, 10 kilometers on a side, but even that watershed, in addition to the soil, is affected by hot spots that may be on the scale of 10 to 100 meters. And you can see in the very lower right there, a single meander within the stream system. So you've got a classic multi-scale problem where the migration, the reactions of the contaminants, in this case also conventional things like nitrate, are affected by small scale behavior. The large scale cannot be understood without the small scale. So this is the challenge to capture that. Next slide. Oh yeah, brief. How much time do I have left?
I think we're a little bit over, so if you could make it through these in the next 2 minutes, that'd be great.
Yeah, I can do that. So just quickly say something about hybrid multi-scale models, which I postponed. Basically talking about separate models. Next slide. This is an example from my colleague Piotr, who's actually trying to do this formally with atomistic molecular dynamics. On the left there, this is actually propagation of a fracture tip into a continuum model, in this case finite element using open foam. And you try to get these molecular and finite element continuum models working together. Next slide. And so you can jump these scales with these so-called hybrid models, coarse graining to mesoscale dynamics. So this is certainly a wave of the future. Next, and hopefully last slide. Nope, I'm going to skip this one. This is too complicated to explain. So last slide is basically somewhat shorter because it comes down to the grand challenge for future contaminant transport is certainly capturing these multi-scale systems where molecular and pore scale determines the plume scale behavior. Also, electrostatic effects I mentioned become important. Any case you've got contaminant transport in nanoporous media, meaning clay rocks. And it may be that hybrid or so-called parallel in time, fine and coarse simulations may be necessary, in particular where the scales are coupled and time dependent. In other words, what happens at the larger scale affects the smaller scale. You've got to formally couple it. You can't just do the upscaling in one direction. So I'll end there. Thank you for your attention.
Thank you very much, Carl. And now I have no doubt after those excellent presentations, you all have probably a lot of questions, and I'll ask Carl, if you want to come up and sit at the table too, to be close to a mic. If you have any questions, please do, as we'll need to use the mics to make sure that Carl and Kevin can hear us. We just got washed in multiple scales, multiple contaminants, multiple processes, and the vexing problem of moving from experiment theory through to models and sampling to check our experiment theory and models. It's really a complex set of problems, very challenging to us. And so I'm going to go around the room here. Please direct your questions to one or more of our speakers. And if you could give me a little help and tweak your thank you. That's good. No, up is fine. I can read as long as it's facing me. So I think, David, you were first. Go ahead, please.
So first, thanks to all the speakers. Very interesting conversation. It seems that there's really two problems here that we need to think about the chemical implications for. One is future prevention, right, to understand how the problems are created in the first place. And there was reference today, and for those of you who were in a session yesterday, about the appearance of surprised materials in water that we don't expect to see. And the second is then dealing with historical issues, which is what we primarily talked about today. As we look at length scales, I understand the tying those together, but what I didn't see a lot about was over time scales. So I'm assuming that when we use the strategy to basically sequester the species so that it's inert, that we're assuming it's going to stay that way for decades or centuries. And I wonder, do we understand the chemistry and the dynamic chemistry of the soil itself and changes that happen that might in fact impact that over the long term? And secondly, could we in fact be creating a concentrating effect that could be in fact worse if there were chemistry that released it later?
And David, was that to all of our speakers?
Yeah, because I don't know who to address it to, because, but yeah.
Peter, Kevin, or Carl, do you have Peter, do you want to take a shot at that, and then we'll see if the others.
Yeah, I could just say something quickly there that I kind of agree that maybe the time scales haven't been addressed as carefully as they should. In fact, in nuclear waste, you know, it's either 1,000 or 10,000 years where you're required to consider that. And so people are actually trying to look at those issues. But also, I think both Peter and Kevin mentioned that some of these redox active contaminants show differing behavior. My experience has been that, for example, uranium is easily reoxidized. So when you look at all those experiments run at the rifle site in Colorado, basically as it reoxidizes, the uranium starts to come out, maybe not as fast as it went on initially, but it comes out. And so basically the barriers fail at some point. A better system maybe is given by chromium, which being more irreversible in terms of reduction tends to stay in that reduced and therefore immobile form. And so you get some more time out of it, although there's some examples of chromium barriers failing as well. And then maybe the most irreversible is the cesium, which once it gets onto those clays and frayed edge sites is very hard to get off, which is good. It means it becomes immobile unless the clays or particles themselves move down the system. But the longer time scales also brings up issues of whether the reactivity of the systems are such that they change over 1,000 years. And so that's not even a simple time scale to address in the laboratory, obviously. You end up resorting to either natural analogs or mechanistic models that you think at least are going to start to capture the long-term behavior.
Can I just ask a follow-up question on that? Do we even understand how the chemistry of the subsurface changes on a decade scale? Forget 1,000 years, or even on a couple of years.
Well, if I could just use one example at the Hanford site, close to the Columbia River, where the groundwater is relatively shallow, it is mostly oxic, and the uranium plume there in the 300 area, so-called, its release, its residence and release is really closely tied to river stage. So annually, you could see pulses of uranium basically becoming more mobile as river stage increases. The hydraulic conductivity in that region of the Hanford site is really high. The water basically just rushes through the subsurface. The groundwater table is very responsive to river stage. And so on an annual basis, at least you can see kind of what you're saying, David, about changes in the subsurface affecting contaminant fate and transport. But your question about longer timescales, I think, is a good one. It's probably one that we don't think about very often because we're so focused on just trying to understand transport mechanism, sort of on the short domain. But yeah, I would throw that out as one example.
Let me just add.
Yeah. Go ahead.
Let me just add to this. We know that agricultural soils are under high nitrogen load, like nitrate. Nitrate is an oxidant, essentially. So we do change the redox potential in soils gradually. When you talk with climatologists, and part of the slides that I showed is that the amplitude of hydrologic events changes. So we have longer droughts, we have higher rainfalls in more concentrated events, which changes very much the redox conditions in our soil. So over time, we see bigger changes back and forth from oxidizing to reducing, which for many contaminants will have an effect. And usually we don't worry about this right now, but how long-term changes in soil.
Well, don't you need to? Because if the goal is to come up with a solution that's going to last, that's a critical problem, isn't it?
Yeah. Yes.
Carl, I think you also wanted to add something. Am I correct?
Yeah, I was just going to say that there is some work. In fact, I was on a project that looked at actually the aging of contaminants, cesium and strontium below the Hanford tanks. But it's a very tricky problem experimentally because, again, immediately talk about even 10 years, that exceeds the typical lifespan of a DOE project of 3 years. So you're trying to address these aging issues and monitor how the reactivity or the release rate would change over time. But people are starting to look at this topic. And probably even more so on soils with organic carbons, things like that.
Thank you very much, Carl. And I'll move to Gerard next, please.
Very good. I have questions for Carl and a question for Peter. And the theme behind my question will be, if this issue was happening again, do we have a good grasp on biodiversity and two types of biodiversity? The first one is amazed by your work on modeling EDL and transport, Carl. My question, I work for Procter & Gamble. I had the pleasure to work with clays coming from the ground, whether it was to clean them from fabrics or whether that was to use bentonite and montmorillonite and try to do good thing with them. And even on one garden, it's different from one side of the garden to the other. So do you think the models are robust enough to predict different clays that exist in the environment, or is it an area of science and foundational understanding that we should dig more into? Should, again, if an issue happens somewhere else, will the tools be robust enough to help to predict? That will be my first question to Carl. And my question for Peter is more on microorganisms. We see microbiome science emerging, and the more we dig into it, the more surprise we have, which is, single properties of one strain is not the same depending of which microorganism. So I will have the question for you is, you were pretty positive to think that we understand biodegradation mechanisms. And I was about really, and but more constructively, do you think that there are some areas of research that we should recommend to do so as to have a better grasp on all, what our microbiome can affect the amazing mechanism on reductase and oxidase you were mentioning? But let me start with Carl.
Okay, yeah, I'll probably just give a brief answer to that, which is say I probably would not use the descriptor robust because that implies mature and fully tested. I mean, I was just fixing bugs in my code last month, so I don't think it's fair to call that kind of model robust. Anyways, but I think the overall approach is promising, and it's computationally viable to give improved descriptions of the system behavior with a single model. Normally what people do is run each contaminant separately with a different set of porosities, even though there's really only one porosity in the system. So it's promising, but there's quite a bit of work remains to be done there.
And Carl, just to put my question, and do you think the model will be agnostic to different types of clays full of magnesium, radionite, ectorite, bentonite? Or will it be work to be done?
Yeah, that's work to be done. I mean, most work has been done on bentonite, but the other clays having different surface charge properties, different interlamellar spaces are all going to behave differently. So we're going to be comparing, for example, in the coming year, bentonite and illite. But they're quite a bit different, but the models are going to be able to accommodate that.
Okay. I'm turning to Peter. Thank you, Carl.
Sure. If I gave the impression that we understand biodegradation, I didn't mean. So we do have the tools today to probe the soil, to see what the genetic diversity we have, what possible enzymes may be there. We can see what enzymes are being expressed, but from there to really understanding and predicting how the microbiome responds, we're not there. There's a lot of work that needs to be done to understand the whole interaction of a very, very complex microbial community. And many of those organisms don't work by themselves. They need a host of organisms to function. And we're not, this is going to be a long research program to really understand that in a predictive way.
Yeah. So great opportunities for research.
Yes.
That will be actionable for this type of problem. Thank you again, amazing work. And if you guys are bored or tired, we can get you working on multi-scale modeling of diapers or fabric spinning. It's simpler and it's not yet done. No, I'm just joking.
Thank you very much. We're going to go with Timothy, then Richard, then Carl, then Jennifer. So Timothy, please.
I'll just usually doesn't matter. But I'm very struck by the synergy between all these talks where you have all these processes in biology that are creating nitrate or consuming it, sulfur, but then we have nitrate enabling mobility, and we have clays where we have ion exchange, or iron oxide where we have titanium basically releasing iron too, but there's titanium being generated, iron being generated on roots of plants. So it seems like there's really an opportunity for a real fusion of microbiome, plants, coordination chemistry here, and I mean, it doesn't seem to me that it's realistic that for us to start taking and making big kiloton scales of absorbance and pumping water, or trying to plant that into the ground. Seems like trying to come up with a natural kind of engineered ecosystem to do this, and at the same time, releasing things like that or playing with nature this way is probably also going to be something that will give some, we should take some pause before we start releasing things in the environment. I just wonder to what degree such an approach would be viable, or it's something that should be considered. It's maybe an open-ended question, but I just wonder, it seems like something where the academies could really help to bring some guidance to how to approach this, if it were to proceed down that type of fusion of biology, plants, and coordination chemistry avenue. So whoever wants to tackle that.
I can start briefly. There is a lot of work going on understanding natural systems and how to use them for water treatment. It goes from the design of engineered wetlands to trying to understand how green infrastructure works. Originally, it's been put in place mostly for hydrology, but we don't really understand yet how best build urban detention pond or a green roof to absorb water, but also to maximize the degradation of pollutants. So lots of people are working on that. In many cases, when you talk about coming up with larger masses of adsorbent and cleaning groundwater by brute force, it's often driven by regulations, and sometimes industry wants to go the proven route as opposed to something more researchy, and EPA is more likely to approve something that's proven. But we see more and more that we are looking at natural processes. For example, work at Berkeley, David, the name will come back, sorry. Many of the pharmaceuticals decay very easily photolytically. So if you have an open pond, wetland, you have a lot of removal of those compounds by photolytic processes, and then the water can infiltrate into the subsurface, and you get rid of much of these compounds. Trying to understand that and how to then set the detention time to get most of the photolytical removal before you get the infiltration is things that people are working on, and quite promising.
Thanks very much. Kevin or Carl, do you have anything to add to that?
Just a brief statement. I think this whole topic of soil microbiome is another grand challenge. I'd say so far it hasn't descended down and got to the pore scale, but maybe that's because that's too challenging. But certainly that's going to be could have been another big grand challenge to have mentioned for the next 10 to 20 years.
Great, thank you very much for that. Go ahead, Kevin.
Sorry, just to follow on with Timothy's thought about fusion of different perspectives, I suppose, applied to the problem. It brought back to mind that I guess it was a year or maybe 2 years ago that BES held a workshop that kind of focused on some of these issues, how to treat the subsurface in sort of a top-down, holistic way that was able to embrace molecular detail where necessary and build it up into larger scale models. And that was the Energy Water Nexus workshop that some of you in the room may have been involved in. I'm not totally sure about that, but that workshop has a report that's pending, and it'd be kind of interesting to see what is there in terms of priority research directions, because I think some of that is relevant to this discussion.
Thanks a lot for mentioning that, Kevin. Carl, did you have a follow-up?
No, I'm good.
Oh, sorry, there are two Carls.
Yeah,
That's the other
sorry,
Carl.
Carl with a K.
Oh, yeah.
So I'm not on the board, but I'm Carl Rockney at National Science Foundation. I run the environmental engineering program, and I wanted to respond to Timothy's question. So funny you should ask. We just sent out a DCL, Dear Colleague letter 18-047 called Signals in the Soil, SITS. And many of the things that you thought, it'd be a good idea for research is precisely what we are inviting right now. This is the first stage of what we consider to be a longer term initiative with solicitations. Right now it is in what would be called EAGER. So these are exploratory grants for research. And the areas that we're looking for, we held a workshop at University of Chicago. And a big part of this is going to be on metatranscriptomics and metagenomics in soils. And some of the four, we're not limited to them, but some of the four things that we're looking for input from the community and suggestions for research from the community are on sensors, novel sensors, low-cost sensors, wireless systems. It turns out it's very difficult to get data through soil from the sensor location up to the surface where we can process those data. Advanced cyber systems and data analysis. We anticipate large amounts of data being generated from these systems, and modeling soil ecosystems. And some of the things that we're hoping to get input and suggestions from the community are on what we would consider to be mid-scale scientific research infrastructure on test beds. So these could be facilities. You'd mentioned, I think, dosing something in the environment is not something you can do very easily, but we're looking for some ideas on these types of things where you could have a user facility where researchers could use that. So perfect timing, I think. So, okay.
Thanks a lot for that, Carl. And I'm aware of our time, and I want to not to have this be my only opportunity ever to be a moderator, so I'll try to stick to our time. We'll go with Richard next, please.
Actually, as somebody who has taught chemistry and complex equilibria and distribution of species to undergraduates and graduate students, nickel and different complexing agents, I'm in awe of what I have heard this morning. The fact that you deal with a nanoscale to macroscale size and with regard to time is really very, very impressive. My comments, though, follow more along what Tim was asking about, and that is when one considers some of the challenges that we have now and discussions that we have with regard to nuclear waste, with regard to possibilities of CO2 sequestration, with regard to bio or rather geoengineering solutions that are put forward with regard to dumping large quantities of iron in the ocean or something else like that. What your work shows me is that there really has to be an incredible caution with regard to undertaking these large-scale solutions. And I don't know if you will agree with that, but it certainly sounds like you do. The answers are not in yet. We can't predict well enough. And if anything, I think this is something that should come from NRC, from the National Academy, that large-scale solutions are not ready for prime time yet to these particular problems. Putting up large-scale sulfur aerosols in the atmosphere as a means of mitigating global warming. Things of this type, approaches in this way, they have to be taken off the table until we really have a good understanding of all of the work that people like you are doing.
Thank you very much, Richard. Peter, Kevin, or Carl, do you have any comments to add to that?
I agree, and in many of these cases, we know the sign. We know how the system will respond, but being able to predict it very accurately, we're not able to do. I thought the case of sulfur, the folks at NOAA GFDL did run the model to predict cooling after Mount Pinatubo eruption. They were surprisingly close, so that was quite encouraging. But watershed scale problems predict changes at a large scale. We are not there. It's very empirical.
Thanks very much, Peter. Kevin or Carl, anything to add? Okay.
Yeah, I was going to say just quickly that I agree too, but I think that some of these things can be undertaken incrementally. Like if you looked at CO2 sequestration, I don't see why you couldn't do a series of pilot studies where you start to look at these things. It just, you have to do it beyond a simple engineering analysis. You have to basically do all the science and associated modeling to make sure that you understand all the relevant processes before you go and take this to really large scale sort of strategy or anything like that. But I think that's possible to do these more pilot tests, science-based pilots tests to improve your understanding and confidence in what can be done.
Thank you very much, Carl. I'm going to take Jennifer next and then see if we have any final comments. Go ahead.
This is just a comment. I work in the multi-phase modeling community in the chemical engineering world, and this is really a comment about what I've observed on some community siloing. So problems like this, you know, that have environmental applications, having to do with transport modeling in the subsurface, really modeling-wise are grappling with the exact same fundamental issues that we talk about in the chemical engineering community with fixed bed chemical reactors, maybe applications like Gerard mentioned, you know, linking pore scale or particle level with continuum. And what I've observed is that it seems like in these two communities don't talk much, but they're dealing with the same types of fundamental modeling issues. And it's just really a comment that I've observed, that these kind of problems are typically, you'll have environmental and civil engineering folks working on. And anyway, there's two communities, and I think they're dealing with very much the same fundamental modeling issues, and you know, which have implications on a whole host of problems.
Very good. Thank you very much for that, Jennifer. And I'm going to take the final 30 seconds to ask a question of our speakers, because we're now, and I can't thank you enough, and we'll give you another rousing round of applause in a moment. I can't thank you enough for starting us out with this foundation, because, and I'm going to assign as homework to my two boards, listening to your talks before we get on with our sessions, because I think they're very important. Just a quick word, if you have advice for, or wishes, shall I say, for our next three series, what would you like to see us tackle, questions that you'd like to see us delve into, some that you've maybe raised here and we should delve more deeply into those, or new questions that these other disciplines might be able to answer, the hydrologists, the geologists and geochemists and so forth. Any words of advice for us as we go forward with these sessions? So I'll ask Peter, Kevin, and Carl to comment on that.
I wish you had told me that a week ago so I can think about it. I think the exposure pathway is an important one to really try to quantify where our major efforts should be. And that is a combination of the hydrology, and then I think one of your boards would have health experts.
Thank you very much. Kevin, how about you?
Well, I think Jennifer basically hit the nail on the head that, you know, there is a lot of expertise in ancillary disciplines to this topic of subsurface environmental fate and transport. That more or less, if we could find a way to catalyze communication between these different disciplines, different schools of and ways of thinking, just bringing people together actually could be the barrier that we need to tackle, make some innovative and real progress. I try to reinforce the message that basically I feel like we've got line of sight to very good, comprehensive, robust models. It's just a matter of time, money, and energy to put ideas down together among different communities and make that kind of discussion happen. And I think we can do that. So if you could try and tackle maybe communication and facilitation of communication, that would be great.
Thanks very much, Kevin. Very important comment there. Thanks. Carl, final word to you.
Yeah, I just also following up on what Jennifer said, I think that's true. And I actually run into the chemical engineers, combustion engineers at Berkeley lab. I was meeting with them yesterday, in fact, but also at exascale. So I think at least in advanced scientific computing, they realize that many of these earth science versus classical chemical engineering topics do overlap. And in fact, I got my start in '88 by talking to combustion modelers. But just to follow up with the last question, I think one of the people on the panel there on your board raised it as the topic of aging and long time scales. And I think that's what spatial scales people have kind of picked up, that the small spatial scales affect the large, and they're starting to handle that. But the time evolution, the aging issue is certainly a big challenge that needs a lot more work. So maybe that topic will come up again in the next couple of meetings.
Thank you very much, Carl. And as I'll ask Suzanne to flip to the next slide, please. And as we do that, I'd like, please, to everyone here in the room to again offer a rousing round of applause to our three excellent speakers this morning. Truly compelling information for us, both here and today, and to take forward with us. And I just wanted to remind everyone of our next item in the series, the Board on Environmental Studies and Toxicology meeting, which will be April 12th. And as I said, you will be hearing from us often with the information to plug into that via the webcast, and also the follow-up when the webcasts are posted. We're going to seek to be able to post also the presentations from our speakers. We'll be working with them on that once we obtain their permission to do so. So stay tuned for that. And thank you all very much again for being part of our little experiment here with this four-part series. Thank you.
Thank you.
Thanks very much.